So yeah, this talk was supposed to be given by my PhD student, Hassan Khan. Unfortunately, he can't be here today because of an immigration problem. Yeah, the credit goes to him entirely. The third co-author, Dan Vogel, he's an HDI prof at Waterloo, so Hassan was the only PhD student on this project and doing all the work. As it turns out, he's also defending today in a week, and then he will be on the job market. So if you're looking for somebody who's strong, who's doing mobile security, please keep an eye on him. So what's this work about? Implicit authentication. What's implicit authentication? The observation is that, as you probably know, when you have a smartphone, many of the sessions are short, right? And so you have to authenticate each time. That's annoying. Right? There's a usability problem. There are security problems. And so people have been thinking about different ways, alternative ways to authenticate on smartphones. And so one of the proposed ways is implicit authentication. And so what you do there is the phone over time learns how its user, its owner behaves, right? For example, the locations the user is going to, the text the user is inputting. And so if somebody else then picks up the phone and starts using it, the phone realizes, hey, it looks like you're somebody else. You're not the owner of the phone. I'm going to lock up. I better be careful. And so there are multiple usage scenarios for implicit authentication. For example, it looks like it would be very attractive for people who currently do not have any authentication at all on their smartphones. And so there are multiple ways in which we could implicitly authenticate people, and one of the ways that has been proposed is touch input implicit authentication, touch IA for short. And so what you do here is you exploit the fact that different people touch their phones in different ways, right? So this is a figure taken from a paper that proposed such a scheme. So they gave the same app to 4 users, asked them to swipe, and as you can see, each of them swipes in a different way. And so the behavior, the differences, as it turns out, are big enough to uniquely distinguish between users. And so the way these schemes work under the hood is you run the touch ID scheme on the phone, and the user you record while the user is swiping, and then you derive various features from these swipes, right? So for example, the location, the length of the swipe, direction, curvature, and so on. And some of the schemes even look at other things like the way you're holding the phone while you're swiping. And so then these schemes have, of course, been evaluated. And what they show is that you can get very high accuracy, like 95%. That's a typical number reported in these papers. Sounds good. And it looks like even industry is interested in these schemes. Some of you may have seen these headlines a few weeks ago. This is a slide that was presented at Google I/O. And so what what Google seems to be doing is they're coming up with different ways. They're adding different ways to implicitly authenticate phone users on the phone. And then they throw them together and come up with a trust score. And so there are different ways like your face, how you talk, how you type, how you move, and how you swipe. So it looks like even Google is thinking about using Touch IA. And we say our message is, well, take a closer look at the security of these schemes. Why? So the way these schemes have been evaluated is what we call a zero-effort attacker, right? So the attacker is not willing to spend any effort on attacking these schemes. In particular, what these evaluations do is they ask multiple users to come to the lab and then gather touch data from these users. And so for a particular user, they use this user's data as positive data, and they use touch data from other users as negative data, and then they build and train a classifier, right? But this is fake. This is synthetic attack, right? These are random attackers that are not willing to spend any effort. And there are very simple attacks that were not evaluated, right? For example, shoulder surfing attacks. Well, as it turns out, there are 2 papers, and only 2 papers, that do mention these shoulder surfing attacks. But they say it's not a big issue. They're not a big issue because they're invisible features. So yes, you can shoulder surf somebody, but then they're invisible features you can't learn from shoulder surfing, like, for example, touch pressure. And of course, there are many other features that can be learned from shoulder surfing, like touch location. The other attack that we were worried about in our work is what we call an offline training attack, right? And so here, you get access to somebody's raw touch data, and then you use this raw touch data to train yourself, right? So you learn to train yourself to swipe like your victim. And so again, the argument was, if in order to get access to this raw touch data, you have to compromise the user's device. And if you have to compromise the user's device, then everything is lost anyway. So why bother? Well, we argue that's not quite true, because there are much easier ways to get access to people's touch data, right? For example, what I could do is I could take my phone, give it to my wife, and then ask her, hey, look at this app, look at these cool pictures on my phone. And while she's using my phone, I gather her touch data, and then I train with her touch data and later attack her phone. Or I tell my wife, hey, download this cool app. And behind the schemes, the cool app is actually collecting her touch data and sending it to me. So our argument is that offline training attacks are not that difficult to set up. And so the goal of our study was how feasible are shoulder surfing attacks and offline training attacks on touch IA. So how did we do this evaluation? Well, first of all, we had to gather some data from victims, right? So what we did is we had two apps, and we let them 55 participants use these two apps. Right? These apps were also used in previous work. So we had a Wikipedia app where users had to swipe up and down, and we had a spot the difference app. So there were two pictures. The user had to spot the differences, so they had to swipe left and right. And for 9 of these 55 participants, we videotaped them while they were using these two apps. And so we videotaped them both from the top, right, while they're using the phone, and also we videotaped them from the side. Next is which touch IA schemes did we use? There are, I don't know, probably at least 5 touch IA schemes that have been proposed. These are the 3 that we chose. Touch Analytics, we chose it because it has a very extensive feature set, right? It uses more than 20 features and gets very good accuracy, 95% or so. LXG, we chose it because it has quite a much smaller feature set, I think in the order of 7 features, but gets similar accuracy. And finally, we chose Silent Sense. It uses touch features, but also it uses the user's posture while he or she is swiping. So we have these schemes, we have the victim data, then the obvious question is, does it actually work? Is our implementation correct? So what we did is we used the data, we used the schemes, some of them re-implemented them, and then we trained a classifier, and these are the ROC curves that we're getting. And as you can see, the results are very good, the accuracy results are very good. So you get a very small false accept rate, and a very high true accept rate. Is feasible, right? So in the upper left corner. And so the next obvious question is, now we have to instantiate these schemes for the actual attack, so we have to choose an operating point. And so there we decided to be conservative. We wanted to give an advantage to the attacker, right? So remember, you can always trade off false reject rate for false accept rate, right? And so what we did is we chose a very high false reject rate, 20%, right? So in practice, what this means, for every 5th swipe of yours, your phone would decide, hey, it's not you, and would lock up. So very annoying in practice. But so we would actually use this in practice, but if you use such a high false reject rate, we get a very low false accept rate, right? That's what we want for our attack. And so I'm showing it on the slide, so what is it, the yellow or green bar, whatever. So the false reject rate is like 20%, and the false accept rate is for 2 of the schemes, it's less than 1%, and for LXGs, I think it's like 3 or 4%. So now we have the schemes, the touch IA schemes. For the shoulder surfing, we're done. We don't need anything in addition. But for the offline training attack, we need a training app, right? So some people need to be able to train themselves, and so we built this app called Mimicry. It shows you a target swipe in green, and then you can mimic this swipe, and then it gives you feedback, like you drew too fast, you have to draw more slowly. Or you are too far to the right, you have to swipe a little bit more towards the left, and so on. Right? So this can be used to train other people's swipes. Then these are the two apps that we used for the actual attack. And so remember, in an actual attack, the attacker is interested in some data, like your photos, for example. And during the attack, the attacker also has to swipe in a way like the victim is swiping, right? So that the attacker has to multitask. And that's exactly what's happening in these two attack apps. In the first, the one on the left, the user is given some text from Wikipedia, and we ask the user a question, and then the user has to swipe up and down in order to answer this question. And for the right app, the user is given a set of pictures, and we tell the user, hey, find the image that is wearing a bow tie, right? So the user has to swipe left and right in order to find the right picture. Some other procedural details. Participants, we invited them to our lab, and then we told them this is TouchIA, this is how it works, these are the different schemes, these are the features they are using, and we also introduced them to the Mimicry app and to the attack apps. The users got rewards. Everybody got at least $10, and then for a successful attack, a participant got up to 25 cents. In total, we had 32 participants who pretended to be attackers. We mounted both attacks. They mounted both attacks, so shoulder surfing, offline training, for 4 victims and for both up and left swipe direction. So overall, we had 512 attacks and 256 unique attacker-victim pairs. So for the shoulder surfing attacks, this is how the setup looked like. So the participant, again, came to our lab. Then he watched the victim or the victim's shoulder surf. We watched a video of the user. Right? This is how we mimic the shoulder surfing. Right? So he watched this video. And the device, while watching the video, the device was lying on a table. The participant could watch the video as often as he or she wanted and from any angle as he or she wanted. And then at some point, the user can say, OK, now I'm done. And then the user, we turned off the screen, and the user launched the attack on the device. For offline training attacks, so we gave the Mimicry app to the user and asked, and again, the user could train. And so there on the left side, you can see this, right, these scores. And so there were multiple rounds. And so once the user passed multiple rounds, the user could proceed to the actual attack. We did a pilot, and one thing we realized in a pilot is, right, so the user had to switch from the Mimicry app to the attack app, and so the Mimicry app has no background at all, whereas, of course, the attack app has a background. And so some people forgot where to put their swipes, right? And so we introduced the pseudo attack phase, where the user is swiping on the background of the actual attack app, but in addition, we give the user feedback how he or she was doing. So what are the results? I'm showing 2 kinds of results in this talk, more in the papers. This is the bypass success rate. This is what we care about. So we have 2 attacks, shoulder surfing, offline training, and y-axis shows success rate. At least 75% of all the attacks succeeded for all the cases. Right? There is no statistically significant difference between shoulder surfing and offline training. It's even worse for silent sense. There, at least 90% of the attacks always succeeded. Why is that? For shoulder surfing, we think it's right because obviously if you do shoulder surfing, you can also observe how somebody's holding the device. We're not sure why it's also so successful for offline training because the Mimicry app does not train people to hold the device in a particular way. We are thinking is because Silent Sense uses a very small set of touch features, like only 4, this makes it very vulnerable. How long does it take to shoulder surf? The x-axis is the shoulder surfing time. Y-axis is the CDF. And so 40% of the people, of the attacks there, we need at most 60 seconds, 1 minute to be successful. And for 90% of the attacks, it takes less than 2 minutes. So it does not take a long time at all. how many attempts does an attacker take in order to succeed, right? So maybe assume you pick up your wife's device, you start attacking it, and then maybe the first time you fail. So you have to wait a little bit, and the next time she leaves the device, you try again. So how many attempts does it take? And again, most people, 70% or even 80% for offline training, they need only one attempt. In 90% of the cases, three attempts are totally sufficient. Some insight at a feature level. As it turns out, acceleration-related features, it looks like they're difficult to mimic. At least for shoulder surfing attacks. We can't make a corresponding statement for offline training attacks, because in offline training, we trained users only for some features, for some easy to comprehend features, right? It's very easy to tell the user, hey, you're swiping too far to the left, move a little bit towards the right. But if the acceleration is not big enough, then it's much more difficult to tell the user what he or she should be doing. So we're not doing that at all. We give feedback only for easy to understand features, right? So we don't know what features are difficult to mimic for offline training attacks. What we do know is that location and duration related features are very easy to mimic. In general, it is much easier to mimic features with the help of the offline training attack, because there you get feedback. Some other interesting results. What if our attacker has fewer resources available, right? Our attackers are relatively powerful, right? So they can take a video of the victim and watch it as often as he or she wants. What if they can't do this, for example? And so this is what we did in the next, on the next slide. So imagine you have an office scenario, and in office scenarios it's probably, right, if you start videotaping your workmates, the workmate may get suspicious, right? And so if you assume a scenario, you see your office mate once, and then maybe you can take notes, but you can't take a video, and then after a week or so, you can actually launch the attack, right? So this is what we did. We told the participants, we showed them the video once, and we told them, hey, you can take notes, right? Then describe the swipe of the victim. And then after a week, we invited them back to the lab. They weren't allowed to watch the video. All they were allowed to do is read their notes. And so then we determined the success rate. Well, non-surprisingly, the success rate goes down, but absolutely only 5 to 10%. So no big deal. There's some other interesting results. I'm going to skip them in the interest of time. And let me conclude my talk. But so when these touch IA schemes get proposed, they often get quite a bit of media attention. So one example, this is from a Canadian news site, is shown on this slide. And so the interesting statement that I want to quote is now is in order to dupe Silence Sense, the criminal in question would have to be a method actor of a caliber greater than Brando, Hoffman, or triple Oscar winner Daniel Day-Lewis. And when someone is that great a mimic, there are much easier and better ways of making money. Well, you don't need to be a great actor in order to impersonate other people, right? So random university students are are totally sufficient. Oopsie, sorry, too quickly. So let me conclude the talk. One thing we learned from this work is that if you evaluate an implicit authentication scheme, it doesn't have to be touch, any kind of implicit authentication scheme. It is crucial that you are aware of the threat model, that you are aware of realistic attack models and take them into account in your evaluation, right? Otherwise, you may believe your scheme is secure, but it's not at all. And for touch IO, it's very easy to mimic other people, and therefore, from a security point of view, our statement is that if you worry about malicious insiders, then you should not be using touch IO. As far as we know, it's not secure enough. If you want to repeat our study, or if you want to extend our study, we have a website. There you can download the apps that we used, the data collection app, the training app, the attack apps, and you can also use the video recordings that we made of our victims. Okay, thank you for your attention.